Welcome! Today, we're cracking open the playbook on 3 really foundational sorting algorithms. Now, you might think you know them, but I promise you, mastering their core trade-offs, well, that's the real secret to acing your next coding interview.
So let's start with a puzzle. These algorithms are, famously slow. They've got a time complexity of O of n squared. So why on earth do the biggest tech companies still spend precious interview time asking about them? What are they really looking for?
Well, the secret is they're not just testing if you can sort a list of numbers. Come on, anyone can do that. They're actually probing for something much, much deeper, your understanding of computational trade-offs. And that's exactly what we're going to unpack today.
All right, so let's meet our players. We've got bubble sort, selection sort, and insertion sort. Now, on the surface, they all accomplish the same goal, right? But as you're about to see, their strategies, their playbooks, they are completely different from one another.
First up to the plate is bubble sort. I kind of like to think of this one as the patient comparer. Its strategy is really simple. Just look at 2 items right next to each other, and if they're in the wrong order, you swap them. And it just does this over and over and over again.
The core analogy here is just so intuitive, it's perfect. Imagine every number in your list is a bubble floating in water. The heavier ones, the larger values, are naturally going to rise to the top, right? Well, bubble sort basically mimics that exact physical process.
And you can see that process laid out right here. With every single full pass through the list, the biggest unsorted number gets bubbled up, all the way to its final spot on the right. This means the sorted part of the list actually grows from the end, from right to left, which is a neat little detail. Okay, next up, selection sort. I call this one the frugal swapper. And its whole game isn't necessarily about overall speed, but about being extremely, and I mean extremely, efficient with one very specific operation. Let's see what that is.
The absolute best way to picture this one is to imagine you're organizing a messy bookshelf. You wouldn't just swap a book with the one next to it. No, what you'd probably do is scan the entire shelf, find the absolute shortest book, and then move that one book directly to the very beginning. So, here's the crucial point. Selection sort does a full pass just to find the minimum element. It does a ton of comparing, sure, but then it only performs one single strategic swap to lock that element into its final place. So the sorted section actually grows from left to right.
And last but not least, we have insertion sort, the adaptive organizer. Now, unlike the others that kind of work on the whole list at once, this one is different. It builds up the sorted section incrementally, just one item at a time.
The analogy here is just perfect. It's exactly like when you're sorting a hand of playing cards. When you get dealt a new card, you don't resort your entire hand, do you? Of course not. You just take that new card and you slide it into its correct spot among the cards you've already sorted. So here's how it works under the hood. It maintains a sorted little section on the left. It picks up the next unsorted item, compares it backwards through that sorted part, and shifts everything bigger one spot to the right to make a gap, and then it just slots the new item right into place. Simple as that.
All right, so now that we know the basic game plan for each algorithm, it is time to put them under pressure. Let's analyze their performance stats and really see how they stack up head to head.
But before we jump into the numbers, we need to define our terms, because it's not just about raw speed. We also have to look at something called stability. A stable sort will preserve the original order of items that are considered equal. So for example, if you sort a list of people by city, a stable sort is not going to mess up the original alphabetical order of all the people from the same city. And believe me, that can be a really important property.
Okay, this table lays it all out. Let's just walk through it together. First, take a look at the worst/average time column. Yep, they're all O of n squared. No big surprises there. And space is O of 1 for all of them, which just means they sort in place. No extra memory needed. But now for the interesting part. Look at that best time column. Both bubble and insertion sort can actually hit O of n, that's linear time, if the data is almost sorted. And now look at stability. Selection sort is the odd one out, it's unstable. These right here are the exact trade-offs interviewers want to hear you talk about.
And this brings us to a super common misconception. You hear it all the time. Bubble sort is always slow. But that's just not true. With a simple little optimization, a little early exit flag, it can check if it completed a whole pass without doing any swaps. And if it did, well, that means the list is sorted, and it can stop right there. This ability to finish early when the data's in good shape, that's what we call being adaptive. Insertion sort has this property naturally, and this simple tweak gives bubble sort that same power.
So the crucial point here is that there is no single best algorithm among these three. It is all about context. It's about knowing the situation and knowing which play to call. So let's look at the specific scenarios where each of these algorithms can actually be the star player.
You know, insertion sort is actually the surprising MVP in a lot of real-world situations. Because it's so incredibly fast on nearly sorted data and has such low overhead, it's often used inside much more complex, much faster algorithms, like timsort. That's the one Python and Java use to sort all the small chunks of the array. Pretty cool, huh?
Now, selection sort has a very, very specific superpower. It's not speed, it's that it is unbelievably frugal with its swaps. It performs the absolute minimum number of write operations possible. And this is a massive deal on certain types of hardware, like flash memory, where every single write operation physically wears down the device. In those cases, selection sort is a lifesaver.
So what about our old friend bubble sort? Well, while you're probably not going to see it in production code very often, its value is actually immense. Its beautiful simplicity makes it the perfect algorithm for teaching the fundamental concepts of sorting. It's the ideal, easy-to-understand baseline that we can compare everything else against.
Okay, it's time to consolidate our playbook. Let's wrap this all up with the key takeaways that are going to give you a real, tangible edge the next time you're sitting in that interview chair.
And if you remember one thing from this whole explainer, make it this. Your interviewer knows you can write the code. What they really want to see is if you can discuss the trade-offs. Can you talk about why you'd favor fewer swaps over fewer comparisons? Can you explain why stability might matter for a certain problem? That is what elevates you from just another candidate to a great hire.
So here it is, your final playbook in a nutshell. Think of insertion sort when you've got nearly sorted data. Think of selection sort when memory writes are expensive. And use bubble sort as your go-to for explaining the absolute basics. Really internalizing this distinction is how you show you're a thoughtful, deliberate engineer.
So I'm going to leave you with this final thought to chew on. We are often totally obsessed with raw speed, right? Big O notation, faster is always better. But when you start to consider all these other crucial factors, things like stability, memory usage, adaptivity, even just how simple it is to implement, how does that change your definition of what makes a truly great algorithm?